Okay everyone, today we will see how to design a lag compensator in control system. Okay, the question is a unity feedback system has an open loop transfer function with g of s is equal to k over s of 1 plus 2s. Design a suitable lag compensator so that phase margin is 40 degree and steady state error for ramp input is less than or equal to zero point 0.2. Okay, first of all, we need to find the value of k. It is given that the steady state error is less than zero point 0.2 for ramp input. Let's take the steady state error equal to zero point 0.2, and we all know that steady state error is equal to the reciprocal of velocity constant error. I'm sorry, velocity error constant. So in order to find k, we need to find the velocity error constant. So kv is equal to 1 by steady state error 1 by zero point 0.2, that means kv is equal to 5. So by the definition of velocity error constant, kv is equal to limit of s tends to 0 s of g of s h of s, and we put the values here and we will get the value of k is equal to 5. See, we are designing slack compensator by using Bode plot. So we have given that g of s is equal to 5 over s of 1 plus 2s. Substitute j omega for s. That is g of j omega is equal to 5 over j omega of 1 plus j2 omega. So from this we need to find, I guess everyone will be familiar with the Bode plot designing. We need to find the corner frequency after that. So the corner frequency, as it is 1 by 2.5 radian per second, and yeah, usual steps. So write the term corner frequency, slope, change in slope, 5 by j omega corner frequency slope is equal to minus 20 because j omega is a part of denominator, so the slope will be minus 20. If j omega if is the in the numerator, or if it is a 0, then the slope will be a positive 20, or if the j omega if it is j omega square in the denominator, it will be minus 40, and if the j omega square is in the numerator, it will be positive 40 of slope. And the next term is 1 by 1 plus j2 omega, and it has a corner frequency 0.5 radians per second, and it's also have minus 20 because the j omega term is in the denominator, and the change in slope is minus 40. Okay, yeah, usual steps of Bode plot. Choose a frequency less than the corner frequency. Here it is taken as a zero point 0.1 radians per second, and choose a frequency which is greater than that, and here it is taken as 10 radians per second. So, and next is the steps to find the gain for all these frequency. So the gain at omega is equal to omega L, that means omega equal to 0 0.1 radians per second. The gain is equal to 20 log of the first term, that is 5 by j omega, that is 20 log 5 by zero point 0.1, that's we got omega equal to 0 0.1 here, so it is 34 dB as per calculation. And next one is at omega is equal to omega c, and the gain is equal to 20 log 5 by j omega, yeah, 20 dB from calculations. And at omega is equal to omega h, that is for 10 radians per second, the gain equation will be like this: slope from the gain, I mean the slope from omega c to omega h, that we have already calculated as minus 40 into log of omega h by omega c, that is log of 10 by 0.5, plus the gain of the gain at omega is equal to omega c. that is plus 20 is equal to minus 32 dB. So these are the basic design of a board plot. Now we need to move into the further design of that compensation and determination of phase margin of uncompensated system. See, and we get, so this is the board plot we have drawn from the calculations, the magnitude plot and the phase plot. Okay, okay, the determination of uncompensated system. Let phi gc is equal to the phase of g of j omega at gain crossover frequency omega gc. Okay, what is this gain crossover frequency? See, we can find it on our board plot, omega gc. You can find omega gc here. This is the gain crossover frequency, and it is, yeah, it is the frequency at which the magnitude plot of the board plot crosses 0 dB. So that is the gain crossover frequency. Now, what is phi gc? What is this term we got here? Phi gc. They said that phi gc is the phase of g of j omega at gain crossover frequency. That means phi gc is the phase of g of j omega. That means phi of this point right here, it is intersecting at the phase plot at the gain crossover frequency, this point, and the phase is phi gc, that is minus 162 degree. Okay, now to the rest of the design. And gamma is equal to phase margin of uncompensated system. And now we saw that phi gc is minus 162 degree and gamma is equal to 180 degree plus phi gc. That is, phase margin is equal to 180 degree plus minus 162 degree, and that's equal to 18 degree. So the current phase margin of the board plot that we have designed now is 18 degree, but the system requires, or the question demands, 40 degree of phase margin, but the available phase margin is 18 degree. So lag compensation is the required one here. So choose a suitable value. That means we the desired value we have here is 40 degrees, as that by omega d is equal to 40 degree, and there must be another value of, that is epsilon shown here, 5 degree more than the what we desire is the theoretical part of that. So the phase margin of the compensated system will be the desired phase margin plus a small value. We can choose it here as a 5 degree for the error adjustment. So yn is equal to gamma d plus epsilon, that is equal to 40 degree plus 5 degree. And now the new phase margin is 45 degree, which means that 180 degree plus 5 GCN, that is 180 degree plus 5 GCN is omega n now. So as we so here that omega is equal to 180 degree plus 5 GC, we have omega n is equal to 180 degree plus 5 GCN, but we don't know what the 5 GCN is, but we need to find out that from here. We know we know gamma n, so we can find 5 GCN, 45 degree minus 180 degree, that is equal to minus 135 degree. This is a new 5 GCN, and this from 5 GCN we can find the new gain crossover frequency, that is omega GCN. See, we have marked the 5 GCN here as minus 135 degree, and we will look where it will intersect in the phase plot. And see here, it intersected the phase plot here, and we need to find the omega GCN right under it. Omega GCN, this is the point of new gate crossover frequency, that is 0.5 radians per second. And now we need to find a new gain corresponding to that gain crossover frequency, that the point B corresponding to that new gain crossover frequency, the point is B, and the magnitude is 20 dB. So see, that's what here the new gain crossover frequency is 0.5 radians per second. Next step is to determine the parameter beta. See, the standard equation for lag compensator is that beta into 1 plus st divided by 1 plus s beta t. So we need to find beta, and the equation for beta is that the equation containing beta is the new gain is AGCN is equal to 20 log beta. From that equation we can find beta because we know the new gain, and we can calculate out that. So beta is equal to 10. Okay, now we are moving to the final piece of the jigsaw. So determine the transfer function of lag compensator. So we need to find the zero of the lag compensator as well as the pole of the lag compensator. Zero of the lag compensator is the 10% of omega GCN. That is equal to 1 by t, and that is equal to omega 0.10 of omega GCN. That means omega GCN by 10, and t is equal to 10 by omega GCN. So we get the value of t. So we get 0. 1 by 20 is the 0 of this compensating transfer function. So the poles of the lag compensator, it is 1 by beta t. So we know the value of t and we know the value of beta. So the pole is 1 by 10 into 20, that is 1 by 200, that is 0.005. So this is the transfer function of lag compensator. GC of s is equal to s plus 1 by t, s plus 1 by beta t. Beta into 1 plus st divided by 1 plus s beta t. Just standardize the equation, that's all. Is equal to 10 into 1 plus 20s divided by 1 plus 200s. So this is a transfer function of a lag compensator, which we need to include as a cascade gain in the loop, I mean like this. So this was the function of 5 over s of 1 plus 2 as with the lag compensator 10 of 1 plus 20s over 1 plus 200s. So this is the compensated block diagram. That's all about lag compensator. Thank you.